think about her when she says I do me, but I fly go right through me. And when I see her dancing, wanna take a chance.
Alright, in example 1, we are supposed to evaluate the integral of x squared plus 1 to the 50th times 2x dx. Here we want to take x squared plus 1 as u, because when you take the derivative of that, you get du equals 2x dx, which can substitute into here, giving us the integral of u to the 50th du. And then from there you can evaluate it to be u to the 51st divided by 51, which becomes x squared plus 1 to the 51st divided by 51 plus c. Here we are supposed to evaluate the integral of x cubed plus 5 to the 23rd times 3x squared dx. We take x cubed plus 5 to be u, since when you take the derivative of that you get du equals 3x squared dx, which substitutes up here, giving us the integral of u to the 23rd du, which becomes u to the 24th divided by 24 plus c, which becomes x cubed plus 25 to the 24th divided by 24 plus c.
Okay, so we have to evaluate the integral of sine x plus 9 dx. We take x plus 9 as our u, take the derivative, which gives us du equals 1 times dx, which simplifies down to du equals dx. Now we substitute the integral of sine u times du, which then gives us the negative cosine u, which then all turns into negative cosine x plus 9 plus c. Okay, so for our own example, we have the integral of cosine x plus 3 dx. We take x plus 3 and change it to our u, which is u equals x plus 3. Taking the derivative, we get du equals dx. So, after we substitute, we get the integral of cosine u du, which turns into the negative sine u plus c. When we plug our u back in, we get the negative sine x plus 3 plus c.
Alright, here we are supposed to evaluate the integral of x minus a to the 23rd dx, which is very similar to the previous problem. Here we take x minus 8 to be u, and then when you take the derivative you get du equals 1 times dx, which simplifies to du equals dx. Then we substitute everything in, and that gives us the integral of u to the 23rd du, which becomes u to the 24th over 24, which when we plug u back in becomes x minus 8 to the 24th over 24 plus c. Here we are supposed to evaluate the integral of x minus 10 to the 18th dx, where we take x minus 10 to be u, and then we take the derivative giving us du equals dx. Substituting it back in, we get the integral, using the substitution we get the integral of u to the 18 du, which becomes u to the 19th divided by 19 plus c, which substituting back in becomes x minus 10 to the 19th divided by 19 plus c.
So, we had to evaluate the integral cosine 5x dx. So, because 5x is inside of cosine, we made it our u. By taking the derivative, we get du equals 5 dx, which then turns into 1/5 du equals dx. Once we have done our substitution, we pull 1/5 through the integral, which gives us 1/5 integral of cosine u du. We simplify that down to 1/5 sine u, which then changes into 1/5 sine 5x plus c. So the equation we are going to now evaluate is the integral sine 7x dx. 7x, because it's inside of sine, is equal to our u. Taking the derivative of u gives us 7 dx, which then turns into 1/7 du if we're solving for dx. Once we substitute, we have the integral sine u 1/7 du. To pull 1/7 through, we then get 1/7 the integral of sine u du. Once then, we have our final equation, which is 1/7 the cosine 7x plus c.
Here we are evaluating the integral of dx over 1/3 x minus 8 to the 5th. Since 1/3 x minus 8 is in the bottom under an exponent, we take that to be our u, taking the derivative of which gives us du equals 1/3 dx, which we can also change to 3 du equals dx, since up here we can substitute it in for dx. This all gives us 3, since we pulled that through the integral, 3 integral of du over u to the 5th. That becomes 3 integral u to the negative 5 du, which can simplify down to 3 times negative 1/4 u to the negative 4, which then becomes negative 3/4 u to the negative 4 plus c, which finally, putting u back in, gives us negative 3/4 of 1/3 x minus 8 to the negative 4th plus c. Our example problem to go with example number 4 is the integral of dx over 1/6 x minus 9 cubed. Since 1/6 x minus 9 is on the denominator and also is under the exponent, we're taking that to be u. And taking the derivative of that, we get du equals 1/6 dx, which in turn becomes dx equals 6 du. From there, we take it back down into the integral, giving us the integral of 6 du over u cubed, which becomes, pulling 6 through the integral, 6 integral u to the negative 3 du, which in turn becomes negative 1/2 6 to negative 1/2 times 6 u to the negative 2, which equals negative 3 1/6 x minus 9 to the negative 2 plus c. Alright, for example 5, we had to take the integral of dx over 1 plus 3x squared. Here we see the possibility of the derivative of inverse tangent being here. So we take the square root of 3x to be u, since that squared would give us u squared. Taking the derivative of that, we get the square root of 3 dx, which becomes 1 over the square root of 3 du equals dx. We put that in here, pulling 1 over the square root of 3 through the integral, giving us 1 over the square root of 3 integral du over 1 plus u squared. Du over 1 plus u squared we recognize as the derivative of tangent negative 1u, so we take that out here as 1 over the square root of 3 tangent to the negative 1 of u, which, plugging u back in, becomes 1 over the square root of 3 tangent to the negative 1 of the square root of 3x plus c. Alright, for our example, again you see the possibility of there being one of the inverse trigonometric functions. So we take 3x out of here to be u, so that when we put u back in it'll be u squared. And that gives us du equaling 3 dx, which, okay, oh yeah, because 3 dx comes up here. So then we come down here and we get the integral of du over 1 plus u squared, which is the function, or the equation for the inverse of tangent, and that's inverse tangent u. And plugging u back in, we get inverse tangent of 3x plus c.
Okay, so the equation we had to evaluate was the integral of 1 over x plus secant squared pi x dx. So what we have here is the sum of the integrals. So what we did is we split them in half. Well, didn't really split them in half, but we separated them to be their own individual integrals. So we ended up getting the integral of dx over x plus the integral of secant squared pi x dx. The derivative of this function right here ended up being ln, the absolute value of x, plus the integral of secant squared pi x dx. So we have to pull a u out of this. So we get u equals pi x, the derivative being du equals pi dx, and to solve for dx we get du over pi. So once we substitute these back in, we get the ln absolute value of x plus the integral of 1 over pi secant squared u du. We pull 1 pi through the integral, which gives us the ln absolute value of x plus 1 over pi the integral secant squared u du. We further go down, simplifying it more, which is ln the absolute value of x plus 1 over pi tangent u. Then we just simply plug our u back into our equation, which gives us ln absolute value of x plus 1 over pi, tangent pi x plus c. So our corresponding equation that we came up by ourselves to go with our previous equation is the integral e to the x plus cosecant squared x over pi dx. So what we did is we split it again, the integral of e to the x dx plus the integral of cosecant squared x over pi dx. We simplify this by having e to the x plus the integral of cosecant squared x divided by pi dx. So for this part over here where we have our integral still, we have to pull a u out, u being x divided by pi. When we take the derivative, we get du equals dx over pi, which then also simplifies if dx equals pi du. So we have, when we substitute this back in, we have e to the x plus pi, which we can pull through, the integral cosecant squared u. This furthermore becomes e to the x minus pi cotangent u, which then simplifies down more after we plug our u back in, e to the x minus pi cotangent x over pi plus c.
Alright, here we had to evaluate the integral of sine squared x cosine x dx. Here we recognize that the derivative of sine is cosine, so we decide to pull sine x as our u. Deriving it gives us du equals cosine x dx, which can plug back in here. So, coming down here, we have the integral of u squared du, which then becomes u cubed over 3, which, plugging u back in, becomes sine cubed x over 3 plus c. A very similar problem where we have to take the integral of tangent squared x secant squared x dx. Here we also see that the derivative of tangent is secant squared x, so we decide to pull tangent out as our u. Deriving it gives us du equals secant squared x dx, which we can plug back in up here. Pulling everything down, we get the integral of u squared du, which becomes u cubed divided by 3 plus c, which gives us tangent cubed x over 3 plus c.
Okay, so the next problem that we are evaluating is the integral of e to the square root of x over the square root of x dx. So we figure because the most complicated part of this problem is the square root of x over here by the e, we make that our u. We take the derivative of the square root of x, giving us 1 over 2 the square root of x dx. To solve for dx, to make it most simplified, or so that it'll fit in this problem over here, we have 2 du equals dx over the square root of x. So we plug this back in over here. We can pull 2 through the integral, and then we have 2 the integral of e to the u du. We then have 2 e to the u, which then simplifies down to 2 e to the x. Okay, so our corresponding problem that we made in reference to the previous problem we had is the integral of e to the cube root of x dx divided by the cube root of x squared. The most complex part of that problem was the cube root of x with the e, so we made that our u. So furthermore, our derivative becomes dx over 3x, dx over 3 the cube root of x squared, which then turns into 3 du equals dx over the cube root of x squared. So once we substitute this back into our original problem, we can pull 3 through the integral, which then gives us 3 the integral of e to the u du, which then simplifies down to 3 e to the cube root of x plus c.
I know this pretty girl, always think about her when she says I do.